After a digression to introduce tools such as maximal function and Reisz potential, we go back to the study of Sobolev-Hajlasz class of functions. Their definition in a general metric measure space is quite easy. M1p includes those LP functions for which there is a non-negative LP function g and a negligible set so that the pointwise inequality holds almost everywhere that is outside that negligible set. The motivation for this definition comes from Hajlasz's original paper, where he observes that M1p of Rn is actually W1p of Rn for the range p strictly bigger than 1 up to infinity inclusive. And also this same claim holds for Sobolev extension domain, which includes a lot of simple domains, Lipschitz boundary domains, and alike. And the impressive point, of course, is that the definition of M1p includes no reference to coordinate system, to partial derivatives, or anything Euclidean. And so the definition makes sense in an arbitrary metric measure space. The reason we introduced Reisz potential and maximal functions was to be able to go beyond the definition and see some of the type of calculations and analysis behind this theorem. And I think that is very beneficial to see some concrete examples, as well as exposing the general theory. Of course, our goal is to avoid too much technicality and not to be or try to be a replacement for textbooks, but there are certain calculations that I thought would fit into this. So I will keep it simple by not getting into all technicalities and only showing the main idea. Okay, the way today what we will show is that given a function u in W1p of Rn, so a classical Sobolev function, it has LP integrable partial derivatives, weak derivatives. So given this, we wish to find the Hajlasz gradient. So we wish to find that non-negative LP integrable function on Rn for which the pointwise inequality holds, so that there exists, well, let's say we understand what we mean at almost everywhere, so that for almost every x and y, ux minus uy is less than or equal, distance in Euclidean space is just x minus y, norm this gx plus gy. So where on earth are we going to look for this function g? Of course, it bounds the functions and it has to do with the gradient of the function, and it will be actually the maximal function of the gradient, which, by the way, is where the name or notation M1p comes from. So to emphasize the link to maximal functions. So let me give you the short answer to this, and only then get into a very, very concrete calculation. So the ingredients needed for this is, number one, the following fact, that if u is a function in W1p of some ball, or similarly it will work if it is just a cube, then at almost every x in this ball we will have this inequality, that u evaluated at x minus average of u over b, which we are familiar with this notation from our discussion of Poincare inequalities, so is less than some constant which only depends on dimension n, integral over this ball And x is of course not the center of the ball, it's just almost every point in the ball of this quantity. So you take the absolute value of the gradient of u and you want to integrate it. So there's this integration parameter y, and x appears here in the denominator to power n minus 1. So that is fact number 1. And now you can see that, recognize that this right hand side is none other than the Reisz potential, but it's integrated over only the ball. So sometimes the set, if we restrict the set, we can denote it this way. So this is the Reisz potential of order 1 applied to the function absolute value of u, then evaluated at x. So this is fact number 1, which after applying a triangle inequality will get us this one on the left hand side. But fact number 2, which gets us closer to having an LP function, is the following, that if you have a ball at some center x and radius r, and you take the Reisz potential of any function, so I think here, let's put, well, we've used every notation, so let's go back just to this gradient u. So this is just an inequality applied to Reisz potential of any function, not just gradients. So the y is less than some constant, again, that depends only on the dimension, the radius r of this ball, and then the maximal function of the gradient u. So here gradient u, if you replace by just some phi, so you see that this is just saying that Reisz potential is bounded from above by diameter of the ball times the maximal function of that function evaluated at x. But note that it's actually, we have a bit stronger inequality where we have truncated maximal function, where we will take supremum over r positive and less than capital R of integral average over balls of that function. So this is by definition maximal function truncated of some function here, gradient u, and the center is always x. So that's the definition of maximal function mr. So two facts that we're not, of course, proving, just using. Number 1, there is this almost every point, the value of the function, the oscillation of the function rather, is bounded by this Reisz potential of the gradient. And then the Reisz potential of gradient in turn is bounded by the maximal function. So this obviously is less than the full maximal function because, well, supremum over a larger collection is only bigger. And here now, the third fact, which we have seen before, is that for p strictly bigger than 1, m is bounded from LP to LP. So putting these facts together, and again using triangle inequality, we end up, so from these we get that for almost every x and y, and well, function is in W1, p of the ball is fixed, so you will get that u of x minus u of y is bounded by some constant, again only depending on the dimension n, the radius of the ball. So you take a ball whose radius is comparable to x minus y, that's where that comes from, and then this will be the maximal function of gradient of u evaluated at x, plus by symmetry the maximal function of gradient u evaluated at y. But then if we define g of x to be just the maximal function of gradient evaluated at x, then g, well, is non-negative by definition, and it is in LP by 0.3 that is barely visible in the screen. So this is in LP, and that gives us that for almost every x and y, we have this. Well, we can also put the constant c up front so that it's absorbed into this g. So this becomes gx plus gy, end of the story. So with this we prove that if you are in W1P of Rn, or just the ball, then you can produce this Hajlasz gradient g of x out of the maximal function of the gradient. Okay, so that was the short answer, supposedly short answer to how one obtains the Hajlasz gradient for a classical Sobolev function. The key ingredient may be, well, all of these are significant, and in follow-up videos we will come back to some of them. But for this one, I want to focus on such an inequality. Okay, points 2 and 3 are just saying that this operator doing this to a function, so gradient u is something we know, it's the gradient of our function, and then doing this to that function seems at first a scary thing, but then it shows that as an operator it is okay, it is just bounded, because this whole thing taking gradient of u to this value only produces an LP operator, because it's bounded by the maximal function, and the maximal function itself is bounded of LP to LP. So points 2 and 3 say that we are quite happy with dealing with such an object on the right hand side. But then the question becomes, how do you even reach here? Or how on earth would someone come up with such an inequality about bounding the oscillations of the function by such an object? Why and how did that x minus y to the power n minus 1 appear in the denominator? So for the rest of the video, I want to focus on this. And in order, again, to keep things within reasonable complexity, I'm gonna do it not for a ball, but for compactly supported functions on all of Rn. For Sobolev functions, you usually prove these estimates for C infinity functions or C1 functions, and then use approximation of W1P functions by C infinity. We know that W1P functions can be approximated in W1P norm by smooth functions in any open set, and therefore proving such estimates is often reducible to proving it for C1 functions. So the reduction, or the simplified version that I want to prove, which already contains the main ideas for the calculation, is the following. So suppose u is a C1 function, so it's classically, even double classically nice function that is compactly supported on Rn. Then for every x in Rn, so this is for every, and for Sobolev functions, so the similar estimate which we later prove, say, for W1P functions, holds for almost every, and this almost every comes from that approximation, because no matter how nicely you approximate a Sobolev function, it's after all can be changed arbitrarily on sets of measure 0, so claims can only hold almost everywhere, because the convergence is pointwise only almost everywhere. But anyway, so when you do it for smooth functions, then the estimates are true for every point. So then for every x in Rn, remember we only want to estimate ux by the Reisz potential of the function, of the gradient of the function. So this is gradient of u evaluated at y, and then x minus y to power n minus 1. So we want an inequality, which was something we needed in the above calculations. But what turns out to be even nicer is that we have an actual equality. So this is x minus y, it's a vector. We dot with the gradient, which is a vector. So this is before we take absolute value. And then you integrate this quantity over Rn. And if you put the right correctional constant, which is omega n minus 1, then you obtain an actual equality. And this is amazing. So this is, well, in one dimension, we have the fundamental theorem of calculus, which gives us the value of the function in terms of its derivative, right? So f of x minus f of y is just integral of derivative from x to y. And because we are compactly supported function, if you take y far away, this will be 0, and then you can replace it with infinity. So we will end up with something like this. But in multivariable, in multi-dimensions, I don't think this is taught anywhere in multivariable calculus, but this is a formula where if you know the gradient, the full vector field, you can recover the precise values of your function from that gradient. Of course, the corollary, which is often what is sufficient for these purposes of pointwise estimates, is that if you take absolute value and then you use Cauchy-Schwarz function, so there's this one, and then when you put absolute value outside this integral, it goes inside and it becomes an inequality. And when you take absolute value of dot, again by Schwarz, it's less than taking absolute value separately, so this becomes x minus y, this becomes gradient u valued at y, and this power 1 cancels 1 power from denominator, so the corollary becomes that this is less than the Reisz potential of the gradient, so x minus y to power n minus 1 dy. So again, for practical calculations, this is often just good enough, but if we have an equality and we can easily prove it, or if the proof of the inequality goes through this equality anyway, then why not get the full equality? So this is in Kinnonen's notes. I will talk about those beautiful notes at some point. Juha Kinnunen has some Sobolev spaces notes. He's from Aalto University, and they are amazingly well written and easy to follow. And he calls this a representation formula. Well, you're representing a function via the Reisz potential of its gradient. Okay, so this omega n minus 1, just for completeness, is the volume. In this case will be Hausdorff n minus 1 measure of the unit ball in Rn. So just the surface of it. So if you are in R2, this will be just the perimeter of the circle, just the boundary. Okay, that is the right constant making this true. Okay. I think this video is now at a good length, and probably we can prove this lemma in the next one. I think that will be safe and less tiring of a video. But keep in mind that we need this lemma to get to this inequality, and this inequality plus the boundedness of this operator by the maximal function was enough to give us the inclusion W1P of Rn inside M1P of Rn. So in the next video, which will be following this one up very fast, we will prove this particular formula, and then we will see other consequences of this, for example, Poincare inequality and Sobolev Poincare inequalities. Thanks for watching this far, and have a great day.